In this illustration, we'll discuss about oscillations of a rod in rotating disk. Here we are given that a smooth horizontal disk rotates about the vertical axis at constant angular frequency omega, which we can see here in this figure. And a thin uniform rod AB of length L performs small oscillations about a vertical axis passing through point A. We are going to find the angular frequency of these oscillations. Here you can see when the rod is slightly tilted from its initial position, it is due to the torque of centrifugal force in the frame of disk, the rod will perform oscillations between the dotted lines we can see here. Now to understand it better, we draw the restoring force acting on the rod when it is at an angle theta. Here you can see this picture demonstrates you how the rod is performing oscillations when the rod is tilted by an angle theta. At its center of mass, a centrifugal force will act onto the rod with respect to the center of disk, and the centrifugal force is m omega square. If this distance OC can be taken as r, this will be r. And the component of the centrifugal force in the direction perpendicular to the rod will have a tendency to bring it back to the initial position. So here we can write at an angular displacement theta from mean position a restoring torque on rod, here you can consider it with respect to disk, is this restoring torque, we can write it as m omega square r sine of theta minus phi, the component of force in this direction, multiplied by this L by 2, the distance of center of mass from point A. And this centrifugal force will result in angular acceleration alpha, with which the rod will have a tendency to come back. So this can be written as I alpha, where moment of inertia of rod about one end where it is hinged can be written as ml square by 3. So it is ml square by 3 multiplied by angular acceleration. Here if you open this sine theta minus phi, for a small angle, so we can write it omega square r, as here m gets cancelled out. Sin theta minus phi can be written as theta minus phi multiplied by L by 2 is L square by 3 multiplied by alpha. Here one L can also be cancelled out. The value of phi we can also calculate in terms of theta. Like in this small triangle, if we drop a perpendicular from point A to line OC, here we can write the length of this will be, as this distance we are given as A, we can write A phi is equals to L by 2 times theta minus phi, as this angle is also theta minus phi. So on simplifying this, we get the value of phi as L by 2 theta divided by A plus L by 2. So if we substitute the value of phi over here, we can see this will be omega square r multiplied by, we can write this as theta minus phi, we can write as L by 2 theta upon A plus L by 2 multiplied by 1 by 2 is equals to L by 3 alpha. Now in this situation here, we can use A plus L by 2 as r. So on simplifying this, we'll get omega square r multiplied by, this is A by r multiplied by theta multiplied by 1 by 2 is L by 3 alpha. So here r also gets cancelled out. The value of angular acceleration alpha we are getting is 3 omega square A by 2L multiplied by theta. We can put a negative sign over here. We can write negative sign for direction of alpha opposite to theta. Here we can substitute this negative sign as these two are in opposite direction, and now we can compare with the alpha is equals to minus omega squared theta, and this will result the value of angular frequency. Here you can see this omega is the angular frequency, omega 1 we can write, and this omega is the angular speed with which it is rotating, the disk is rotating. This omega is the angular speed with which disk is rotating, and omega 1 is the angular frequency of small oscillations of rod, which can be written as root of 3 omega square a by 2l. So this is the final result of angular frequency of oscillations of the rod.